the more observant of you in the audience may have noticed that I am not Yitzhak Loroff. I apologize for that. You're trading an Orthodox rabbi for a pudgy Puerto Rican lady. But I'm going to be talking to you about something that I think is pretty cool, and I hope you'll enjoy it. First of all, I've had a lot of really cool moments in my career. Having this many people actually wake up at 8 o'clock in the morning in Las Vegas is definitely one of the tops. So for those of you who don't know me and who I didn't pay to be in the audience, my name is Samantha Quiñones. You can reach me on Twitter at @IEatKillerBees, or you can check out my website, SamanthaQuiñones.com, if for some reason you find that easier to remember than @IEatKillerBees. How many of you realize that AOL is still a thing? Yeah. Don't shake your head. I'm a principal software engineer at AOL. I work on the AOL Media Platform. So even if you think you never use AOL, anytime you go on Engadget.com or TechCrunch or Huffington Post, guess what? You're using AOL. And your grandparents are probably still using AOL.com. I have the traffic numbers to prove it. I joined AOL about a year ago. And I was actually brought on for a specific project. Originally, when they reached out to me, I wasn't all that interested in going to AOL because, like you, I had no idea what that company was doing or why I would ever want to go work and sell dial-up access. But during my interview process, I was asked a really interesting question. And it's a question that I really like to get in engineering interviews, and it's the kind of question that I really like to ask in engineering interviews. How would you let editors test how well different headlines perform for the same piece of content? This is a good question because it kind of lets you approach somebody's problem-solving skills without having to get into things that need to be memorized. So I can talk for an hour about hiring practices and why I don't like that. But this is a cool question. Essentially, this is a question about multivariate testing. And multivariate testing is one of the kinds of metrics that we need to collect and analyze at a company like AOL in order to make ourselves profitable, right? So we're trying to sell you soap. Essentially, that's our business model. Well, soap and tampons and hair dryers and all this kind of stuff. So we want to make sure that you're seeing the right ads when you're trying to watch like our little Steve Buscemi videos that we put up. So doing this kind of metric collection is really important. There are a lot of different kinds of metrics that we collect and look at. We want to look at sort of traditional metrics, like performance metrics, like are requests being handled efficiently? Are we using the hardware resources, the compute resources that we purchase? So in the past, we might be talking about like how much power are we using in our data center to run all the servers. Now we're talking about sort of paid-for compute hours on some public cloud. Are we allocating adequate resources at every layer of the stack? Do we have any areas that are bottlenecks? Are we using cache efficiently, right? Is our cache hit rate high enough? This is very, very important for us. In fact, it's something we pay a lot of attention to. So we use New Relic as one of the tools that we use for metrics. We like to see this graph. So this is a CPU time per request graph. And you see as the number of requests being handled per minute increases as we move towards the right, the actual CPU time per request drops. And it does that because our caches are warmer the more requests we're fulfilling. We can do things looking at stack performance. So this stack that I'm talking about is a pretty big stack. It's up to about 250 million page views a day. So it's beefy. All of the software that's involved in creating, editing, managing, and rendering content is all PHP. So if anybody tells you PHP can't scale, they're lying. It's not the prettiest PHP in the world. Sometimes you do have to sacrifice a little bit for performance. We're really, really pumped about PHP 7. We're thinking we may be able to shut off maybe a third of our servers, our render servers, so that's really, really exciting for us. But we can use graphs like this from New Relic to kind of see where our time is being spent. So like the big blue bar there is actually just PHP running, PHP functions being executed. We have calls to memcache, so we use memcache sort of as an on-server local cache. You see all those web external calls? Those are actually calls to our federated caching network. So we have a network of all of these cache servers that are existing in all of our different data centers and also in AWS. And they're all federated across those network boundaries, sharing information back and forth. So most of those web external calls are calls to that caching layer. And then MongoDB. As you can see, it's the smallest sliver because it truly is web scale. In addition to like actual, like real electrons flowing through wires, we're really looking at perceived user performance, right? So how long does it take for a page to be ready for the user? Is the page responsive to user input? Does the page require just an excessive number of requests to complete, right? We look at that from a technical standpoint, but from the end user standpoint, that's more time of the spinning bar, right? And it gives the perception that the page is slow. And in fact, there's been some interesting studies about sort of the psychology behind this. For delays that are under 100 milliseconds, it's actually a little bit too fast for the human brain to really pick up on. It's not, I won't say that you can't notice time smaller than 100 milliseconds, but generally speaking, in the course of using a website, you're not going to notice that. Under 300 milliseconds, the delay becomes a little bit perceptible, but it's no big deal. And in fact, you have about a second where it just seems like the system is working. And in fact, in some applications, I used to work in finance, in some applications, it's actually to your benefit to add in delay during security operations because it gives the user a sense that the computer is working really hard to protect their data, right? And in some cases, I guess that's actually a real thing. That's why we talk about hashing passwords and using slow hashing algorithms, right? So there is some merit in there. Between 1 second and 10 seconds, you're in this situation where the user sees the system as being slow. You're going to start burning off users very, very quickly during this period, and really nobody is left after 10 seconds if they have a pulse. Amazon did a study of the effects of latency. This was, I have to look at my notes, this was in 2006. They studied how latency affects sales, and they found that each additional 100 milliseconds of increased latency resulted in about a 1% drop-off in sales. So I don't know what Amazon sales figures are, and I don't see anybody in the audience who works for Amazon that I know of. Let's say they're making $2,000 or $3,000 worth of sales every second. A 1% drop-off can be huge for them in terms of revenue, especially in a tight industry like retail. You might have heard of Google's search experiment that they did in 2009, where they actually intentionally put little test delays inside of their search results, and they found that each additional millisecond of latency had a drop-off in the number of searches that got performed per second. So Google makes their money basically the same way that we make money. We put ads for tampons on the web, and you look at those ads, and hopefully you buy the soap flakes or whatever, and we make money from that. So the less impressions we make means the less times we put an ad in front of your eyeballs, means the less money that we make, and that's bad for us because we like money. We also spend a lot of time measuring user behavior. So we're trying to understand sort of the paths that they take through our content. We're a media company. We're producing print media on the web and video media. So it's important to see, like, where do they start the video? Where do they stop the video? Where do they pause? We can't really track where people's eyes are, but we can track where their mouse is on the screen. And we use that kind of as an indication to tell us, what are they looking at? Where are the hot places on the screen? Where are good places to put ads? Where are the good places to put the content that you really want to draw them to? If people are paying for sponsored content, which I agree is kind of a gross thing, but it's a reality of the media landscape right now, you want to make sure that you're positioning those pieces where people are actually going to see them, right? Because you need to make money somehow. This was from Dreamscape Multimedia a couple years ago. This is kind of like the F map, and you might have seen this if you're like a UX designer or a UX kind of person. It just shows a heat map of kind of where people's attention fall on the Google searches, and you see it's all up in that top left corner, right? So that's kind of why Google structures their responses that way, right? It makes a lot of sense. Another thing that's important, how many of you guys do multivariate testing for your users? Okay, I see a couple of hands, great. So, I mean, we're doing multivariate testing. I have a sciences background. You sort all your users into groups. You have a control group that gets the content basically unaltered. You have one or more groups that get treatment groups that get the altered content, and then you're going to measure all of those kind of behavioral statistics, like their click-through rate and how deep they're scrolling and all this kind of stuff to see which pieces of content perform better. And there are some things that we don't really generally lump in with metrics, which are metrics. We're talking about exception information. Application is running, it's generating exceptions. They may be harmless, they may be harmful, but generally there's some kind of performance impact by having those exception states fall into. So it's important to monitor and get data about those. Load monitoring is very, very important. A lot of what we do is a lot of what we use New Relic for is kind of this these back-end application performance kind of things. One of the cool things about working at AOL is that we're kind of on the forefront of digital media, right? So digital media, we kind of have a problem in the media industry. Like, we don't really know how to make money. And all of these different companies, the big players in media, are trying to figure this out. So it's kind of cool to experiment and try to find ways to actually generate revenue because people want to read stories. They want to read cool information, articles, news. They don't necessarily just want to put out their credit card and pay for it. So we're trying to do things like augmented intelligence for the content creators. So we have very, very talented staff of people that work at Engadget and Huffington Post, and they're really, really passionate about the things that they talk about and write about. But we want to give them tools that help them approach their content generation from a revenue perspective. Like, can we give them information saying, the content that you're writing is similar in profile to this other content that you've written, and it performed like this. So we can make a qualitative prediction that this new content is going to perform well. It's worth your time to write it. We want to do things like quality prediction, which takes sentiment analysis. We need to kind of examine how people are receiving content and find a way to quantify it, right? So these are some difficult problems that we're working on. One thing that I like to talk about is, like, what if content could change itself based on the weather? We have all this data about how content performs. We put a piece of content out there, and within seconds, we know who's clicking on it and where they're clicking on it, how long they're reading it, how deep they're scrolling into it. Can we find changes based on the environment that the particular reader is in, right? So there's some interesting questions here. These are essentially data questions, right? Big data questions, and this is a problematic term. I've worked with big data since before it was really an industry term. In the 90s, I was at Visa. We were working with data on the scale of hundreds of terabytes, which in the late 1990s was a hell of a lot. We did this through the use of literally a floor full of tape robots, right? So huge, huge, huge volumes of data. That's one way that data is big, but financial data is fairly simple. It's essentially columns of numbers, very, very easy for computers to handle with. So data can also be very, very complex. And the problem that we have at AOL is more of a problem of complexity, although we do have a fairly big amount of scale. So when I say that, our data collection system, which I'm going to describe to you, is currently collecting on the order of 1.3 billion events every day. Each of those events is a complex schemaless data blob, and they average about 40 different data points per event. So this really, really depends on sort of the device that's generating this information. We get different information from a desktop browser than we get from a mobile device. We get different information from services and APIs that are running in the application. They're all feeding to this single data collection pool. So each of the events is a little bit different. That's a lot of where the complexity comes from. We're receiving these events on the order of about 15,000 per second. Now, this number's a little bit out of date. We're averaging a little bit closer to 20,000 now. This will spike up to 25, 30,000 a second. So it's a lot of data really, really fast. So that's, on average, every second, about 600,000 data points that we have to index, right? And if we want to talk in terms of megabytes per second, it's between 25 and 30. So it's a fairly large data pipeline. It's nothing like maybe what Twitter or Facebook is dealing with, but it's big. So I want to talk to you, and essentially the heart of this session is talking to you about how we approach this particular problem of dealing with this data in real time. We collect our data through the use of collection servers. These collectors live on the internet. They're addressable. It's b.aol.com if you're ever on Engadget.com or something, and you open up the Chrome Inspector and you see little calls to b.aol.com. That's the data. It's just little JSON objects. You can look at it. I promise you we're not doing anything creepy. If we were, I would not be cool with that. But we're collecting all this data, and it hits into these hundreds and hundreds of collection servers. And all these collection servers, which are just little thin Java clients, they do some kind of filtering. They're doing like device analysis. They have some logic in them to sort of filter out spam, because again, these services are just openly accessible on the web. So we get a lot of garbage data. and then they dump all of that data into a huge RabbitMQ farm. On the other side of RabbitMQ, we have Hadoop, right? So for those of you who aren't familiar with what Hadoop is, it is a framework for distributed storage and data processing, right? It's designed to make it easy to manage very, very large data sets, and it does that through two cool ways. We have really well-documented open-source common libraries. A lot of this stuff is like Apache software, right? So a lot of these are Apache projects that we're talking about. And it's optimized for commodity hardware, right? So I was saying before, we used to deal with big data at Visa. We were doing that through the use of literally hundreds of millions of dollars of customized Hitachi and EMC data management hardware, right? Most people, or most companies, organizations don't have the resources to invest in that kind of capital. Thankfully, with stuff like Hadoop, we can run this on commodity servers, right? A lot of people are running their Hadoop stacks in AWS now, right? Because it's really, it's just compute hours, right? And we can do that. Hadoop is built around the HDFS, the Hadoop Distributed File System. It's modeled after the Google file system. Essentially, this just takes logical files and stores them across multiple systems. It's cool because it's rack aware. It'll try to put some data locally, and it'll try to write some data to machines in a different rack, to give you a little bit of redundancy. The big thing about Hadoop for application programmers is that there's no read-write concurrency. This is not a data store that you're going to read and write data to at the same time. It's not MySQL. I mean, you're going to have a bad time if you try to do something like that. Generally speaking, we access data in Hadoop through MapReduce. There are some really cool tools that I'm not going to talk about, things like Apache Spark right now that are really changing the way we get at the data that we're dumping into things like Hadoop. But generally speaking, still you're running like either Hive or Pig jobs, and you're doing MapReduce. MapReduce is just a framework for parallel data processing. I'm going to assume that most people are familiar with this because you probably work in PHP, or at least JavaScript, and both PHP and JavaScript implement map and reduce, which are elements of this sort of framework. This is a really, really contrived example in PHP where we have a document, it's about 10 words long, and we're going to run this through a map function. And all that map function is going to do is count each time we find an instance of a particular target word. We're going to look for the word is. And this is going to produce just the counts. All it's doing is how many times did I find it in this document. We can then take that information and pass it into a reduce function, which will do the math and sum it up, right? So this is, like I said, this is a really, really contrived example. But if you imagine that this document, instead of being 10 words long, is 10 million words long, we wouldn't want to start at the beginning of that document and read through it word by word by word by word. It would take forever. What we can do instead is take that document, break it up into a million different documents, give each of those a million different documents to one of a million different servers, right? These are just funny made-up numbers, but you can give each of those smaller documents to a server. They can run the map function on that smaller piece of the text, return the counts. We take those counts, give them to a bunch of servers to run the reduce function, and we get to our final number much, much more quickly than we would if we'd started at the top and just continued through to the end, right? For us, Hadoop has some important limitations. Like I said, we're not using Apache Spark. If you're interested in why, I'm happy to talk about that after, but usually everyone asks, have you heard of Spark? Yeah, I have. Hadoop jobs are batched, right? They take a significant amount of time to run. Like I said, we have one collection infrastructure at AOL. My team is one of many, 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 many teams. We have 4,500 people at AOL. Most of us are engineers, so we're all trying to get at this data at the same time, so we have to play nice. We can only get access to the data at certain amounts of time. We only get a certain number of servers to run our queries on, so it can take a while. And in fact, it can take us more than an hour to get data after it's collected, because it goes into RabbitMQ, and I kind of glossed over this, but it goes into RabbitMQ, and it goes into like an H-based database where it kind of sits for a little while it gets pumped into Hadoop. So it can take about an hour for us to even be able to get to data, and then we can run a query that takes 2-3 hours to run. When we're trying to answer questions like this, how can we tell editors how well different headlines perform for a piece of content? That is not a question that we can wait 4 or 5 hours to answer. One of the things that makes media hard is that most content is only relevant for 24 hours. We always talk about the 24-hour news cycle. That's not just a thing that news does to be terrible. It's just there's so much competition for people's attention, and everybody wants to sell you soap flakes, right? So we have this constantly roiling cycle of news. Most content becomes completely meaningless after a day or so. And interest really peaks within a few hours, so that's what our editors are interested in. Well, if I go to my customers up in New York, and I say, like, what kind of information are you interested about articles? What kind of traffic information, demographic information can I give you about the content that you produce? They're going to tell you, I want this, this, and this, but I really need to know about it today. Like, I don't care what happened yesterday. I need to know how this article is performing over the last 60 minutes, right? So we have this problem of all of this really cool data that we're collecting, and we have a really awesome team of smart engineers and data scientists who collect it and will do really cool things with it, but we need access to it in near real time. So before I mentioned that we have our collection servers and then RabbitMQ, we also have another guy that sits off to the right of the RabbitMQ farm. We call them streamers. Essentially, these are our Java instances that stream everything that gets written into RabbitMQ live. So it's been filtered by the front-end collectors. We're not really getting all the kind of garbage spam, like people fuzzing our sites and stuff, but we're getting a live, raw stream of all of this data that's flowing through the network. The first time I ever opened up my browser and hit the streaming API, I didn't know Chrome could crash that fast. It was kind of a shocking moment. It's a ton of data. So I said before that I came to work at AOL on this particular project, and it was actually really an interesting experience because I've never taken a job where I knew exactly what I was going to be working on before I even started working there. And in fact, in the weeks leading up to my start date at AOL, I had a number of really cool conversations with my future boss, exactly about what we were planning to do, kind of brainstorming ideas on how we were going to approach this problem. So I had the unique opportunity when I first arrived on day one, and I got my CD so I could sign onto the network. I knew exactly what I was doing, and I could sit down and start working right away on version 1. The first thing that I tried doing was taking that streamer, which is it's an HTTP API. You connect to it over HTTP, and it just starts streaming data at you. So I connected to it with a Node.js process, just creating a Node.js stream. And as this node stream comes in, I'm breaking it apart by line. So I'm literally just like looking at the stream and looking for a line break in the stream. Each time I see a line break, I generate a record. I push that, I generate basically a native JavaScript event. I have a bunch of visitors, little pieces of code, very small modular snippets of code that each pick up that record, do something with it, do some processing, generate a statsd object. So I kind of mentioned statsd over there on the right. Generates a statsd object, and then pushes it out to statsd. If you're not familiar with statsd is a really, really cool tool that's used to collect and aggregate data. Like, I think it came out of Etsy, but if you've ever heard of Datadog, like they're like really on board with statsd. It's a very, very powerful tool, and I thought this would be a great way to approach this. So just for the record, this is the only piece of code from version 1 that made it through to production largely intact. So I guess if I got one thing right about the prototype, was the idea of doing these small modular chunks of code that do the actual filtering, although they ended up living in a very, very different space. So version 1 took me about a week to build, and in fact, I took this on my 7th day at AOL. I didn't think to take a video. But for a proof of concept, it's not too bad. I have this map of the world, and every time somebody looks at an article, it gets added to a count, and then we refresh this map every 250 milliseconds, and the colors change, right? Ooh, big reveal. It proved that we could actually take something meaningful out of this data stream. So I consider it a success in that respect. We were only able to process 300 events a second, which means that to put this into production, we would have needed about 70 servers just for collection. And right away, a problem with statsd reared its ugly head because the statsd data format basically creates a ton of data redundancy, and it reduces data richness, right? So when I get a record in from the collector, I know that a particular person in a particular place looked at a particular piece of content, right? After going through StatsD, all I know is that a particular piece of content was looked at, that a particular piece of content was looked at by someone in this particular place, right? I lose the connection of who that person is. Not that person specifically, but the concept of a single person, right? So version 1 is not going to do it. As I started working on version 2, I started thinking about, so I spent a lot of my time just really doing system architecture. Actually, coming back to this job was the first time I've been coding full-time in quite a while. And I started thinking about how to approach this from an architectural standpoint, and I kind of created these two concepts. This is not a real concept that anybody smart came up with. This is just me talking. But I have this idea of transits, which are going to be very short-term, in-memory, volatile places for data to live. Data that has a short lifespan for a couple seconds. And having terminals, that's where the destination for the data, where data goes to get stored or abandoned or pushed onto another terminal, or onto another transit, rather. And I decided that for this application to work, I wanted to create a network of transits and terminals. And I didn't want any single node to act as both a transit and a terminal at the same time because the load on transits is so high. StatsD, in addition to the problems that I mentioned, acts as a transit. It takes data and it passes it along. But it also acts as a terminal. It aggregates the keys in memory. It waits until a threshold before it pushes it on, right? So StatsD obviously is a misfit in this. So I went ahead and replaced it with RabbitMQ. So if we're still following along, back to the left of the screen here, we started out with a Java collector, and then RabbitMQ, and then an HTTP streamer, and then Node.js, and then another RabbitMQ. Right, so we replaced RabbitMQ, and I made some changes on the receiver side of things too. Node.js is really, really fucking fast. I love Node.js. The native eventing in Node.js is not the fastest thing in Node.js, and when you're trying to process thousands of records a second through a Node.js process, you definitely run into that bottleneck. So I removed the eventing. Essentially, I'm still doing the same thing, cutting records out of a stream as it's coming in. But each new data record that I create, I would then just push it onto a process chain, and that process chain would engage each of the little edits along the line, generating an enriched record at the end. And that entire enriched record is what we push out through the other side into RabbitMQ, right? So now we're keeping the data together. I still know that a particular person looked at a particular piece of content on a particular device in a particular location. We just kind of cut away all the fluff that we don't need, and we do some pre-edits. Like we look at the device that they were looking at, the user agent that they accessed the data from, and we parse it out and figure out kind of what they were doing. We look at the referral information and try to make some decisions about whether this was an internal referral, so whether it was like a link on Engadget to something on Daily Finance, something like that. And then it gets pushed onto RabbitMQ. I mentioned RabbitMQ a bunch of times in the hopes that you guys are familiar. I can kind of see you, so if you stick your hand up and you don't know what RabbitMQ is, I can give you the 5-second explanation. I don't see any hands, awesome. So RabbitMQ is a really, really lightweight message broker, and what I like about it is two things. It lets us do very complex message routing without any application level logic. So the other thing I was looking at instead of RabbitMQ is something called Apache Kafka. I don't know if you guys are familiar with Kafka. RabbitMQ's routing facilities are a little bit more robust, and because I'm collecting billions of events a day, I really don't care all that much about losing some of them. So if I drop some on the floor, it's not the end of the world. RabbitMQ also can buffer about 120 seconds of traffic, right? So if I have a bottleneck anywhere in the network, data can sit in RabbitMQ as kind of a buffer for a little bit of time, which is really, really important for me, because my life gets very bad when RabbitMQ fails. So version 2. Got rid of StatsD, replaced it with RabbitMQ. Eliminated the eventing in JavaScript, which improved its performance quite a bit. I'm keeping all of my data records together. Sadly, I lost that nice automatic integration with Kibana, the ElasticSearch front end. So that was sad. At this point, things were better, but I found myself being really concerned with things like processing arrays in a loop and trying to figure out if it was more efficient to shift elements off of the array, or to clone the array and slice it. When you start doing these kinds of micro optimizations in your code, by the way, the code on the right is like 10,000 times faster than the code on the left. When you start looking at things like this, you know you're setting yourself up for failures in the future because you're going to have a bunch of crazy code. And in fact, as I was working on version 2, I found myself constantly having to add code to cover weird edge cases everywhere. Right? So it was getting very, very brittle. It did perform twice as good as version 1, as the proof of concept. So it got up to 600 events a second. Now we're only down to 35 servers needed for prod, which is a much, much more reasonable number. But all this micro-optimized code was kind of giving me heartburn, right? I was not happy with it. So I decided to drop version 2 and move on to a third version. It was clear that I needed something on the collector side, right, on my receiver side, that could handle very, very high throughput. Something that would let me use a multi-threaded worker pool, which you can do in Node.js, but is not the easiest or cleanest thing you can do. Something that would let me access very, very large memory buffers, do static and dynamic optimization, something that would let me manage very large volatile memory data sets in memory. And I also wanted something where I could eliminate any of the processing overhead. I was going to turn the receiver into a pure transit. So all of that logic that's doing the user agent parsing and the referrer parsing, I was going to get rid of that, or at least move it. Also, I couldn't use Golang. Nobody on my team was familiar with it. I don't want to create a buzz factor. Couldn't use Rust because no one on my team would even consider learning Rust. And I don't hate myself enough to use C. So I was back to Java. And it's funny because when I first approached this and I first started talking to the data team about it, they said, you're going to want to build your collector in Java. And I said, Java? It's 2014, kids. It's all about Node.js. It's the Node.js world. Java is really, really awesome. I think Java gets a bad rap for the same reason that PHP gets a really bad rap, in that there's so much shitty Java code out there and so many horrible Java frameworks. Java itself is actually pretty cool. So you have really, really good static and dynamic optimization, both at the source to bytecode level and in the Jet compiler itself. There are open source clients for basically everything in the universe in Java. And within AOL generally, and specifically within my team, there are several people who are familiar enough with Java that if I were to drop dead on this stage, they would understand what the code was doing, right? So that's a very, very important architectural decision. So let's look at version 3. Sorry, it is so dry in Las Vegas, it feels like my throat is going to jump right out of my neck. In version 3, we still have the receiver. Now that receiver is written in Java. And over here on the right, up on top of Elasticsearch, we have this thing called the processor router. That is essentially the rest of the processing that was in that Node.js process, sort of removed into its own standalone service. I annoy all my coworkers like I am like the queen of microservices. So I have all these tiny, tiny little repositories of code everywhere that do one specific thing. So we'll talk about the processor router a little bit. From a logic standpoint, from like a data flow standpoint, it's very, very similar in Java as it was in Node.js. So the data comes in, we're still reading the stream, we're cutting it off into records each time we see a line break. This time we're squirting all of that data into a work queue. So I have a bunch of worker threads that are all warm and happy and running on the machine. Each one of them essentially has a giant linked list, and we just pump shit into that linked list, and they sit there and do their magic and push it out to RabbitMQ. You guys are probably not all that interested in looking at the code, but see, this is my Java code. This is my shitty Java code with no XML configurations. It's pretty lightweight. It's not doing anything particularly crazy. What we're doing is just creating some threads, pushing data onto it. Each time we get a record out of the receiver, we push records onto it. Really, really simple. I call this the ketchup bottle diagram, but essentially this is all that this receiver is. It's just network input on one side, a bunch of linked lists, and then network output on the other side. So there's nothing going on here except just taking data, cutting it into chunks, and then pushing those chunks out the other side. I got a little bit of a performance boost doing this. These receivers could collect about 2,600 events every second. It means I would need 10 receivers for prod. In reality, in production today, I have 12, so pretty close, right? So big win. Thank you for coming to my talk. Now, I want to talk to you about some of the other decisions that I made. One of the things that people always ask me is, why are you using ElasticSearch? Is anybody not familiar with ElasticSearch? Awesome. ElasticSearch is a really cool search engine. It's a sort of the spiritual successor to Solr, but not shitty. What I like it as is just a really highly distributed storage engine. Like it's just a great document store. It clusters really, really nicely, and it has all these really cool built-in aggregations, because I don't like doing math. What kind of aggregations do we have? Geographic boxing, radius grouping, right? We can say, given a geographic area on the planet that's defined by these coordinates in a square, give me everything that happened in that area, or give me everything that happened within a 50-mile radius of this particular point on the face of the Earth. We can do time series aggregations and histograms and standard sort of min, max, average statistical evaluation. I really need to update this slide. MapReduce has been available since like ElasticSearch 1.5. We're on 1.7 now. This lets us answer questions like how many users looked at a post on an Android tablet in portrait mode within 10 miles of Denton, Texas. Or what is the average time from the start of a page load to the first click for readers on Linux desktops between 3 a.m. and 5 a.m. In media, we call that the money demographic. Or given two sets of link texts, which has the higher click-through rate for a randomized sample of readers on tablet devices, right? That's the multivariate question, right? And the important thing, all of these tools together, they let us go browser to browser in less than 5 seconds. When I say browser to browser in 5 seconds, I mean you click on an article on Engadget.com and an Engadget editor at 770 Broadway in Manhattan sees that you clicked on that within 5 seconds. Not you particularly, but the stats reflect that you did that. So that's fucking fast, right? We're talking about from like 4 hours down to 5 seconds. I think that's a pretty big improvement. And I told my boss this, and I'm like, isn't this fucking awesome? Aren't you glad you hired me and paid me stupid money? I'm cool. And he said, well, is that real time? I want you to understand, I joke about my boss a lot. He's a really, really brilliant guy. I love him to death. It took me a while to understand what he was really getting at. So all of this stuff that I built was really, really cool. But what he was looking for was live analysis of data as it's being collected. What he really wanted was active visualization of very, very tiny trends in the data. I didn't understand why this meant anything to him, right? Especially because, like I said, coming from a sciences background, like I know that small sample sizes for data sets, especially when coupled with very small analysis windows, is basically how you do bad science. The data volumes are huge. End users can't comprehend this stuff. It has to be aggregated to make any sense to people. And like I could demonstrate when I first connected to the streamers with Chrome, end user hardware and end user network connections can't handle a 30 megabyte stream of data coming into them, right? So I didn't really see the value in this. But it's my job to solve weird problems, so I added a WebSocket server over here in the bottom right-hand corner. I'm going to try to send something over WebSockets to a browser and draw pretty pictures on the screen. This is kind of, from a logical standpoint, what the WebSocket server is doing. It's just reading that RabbitMQ stream, reading that queue in RabbitMQ. And it's doing random message selection. So obviously, I can't handle the full stream, so it's just pulling out one every, I think it's every 10,000 events. And we pump those onto an event bus, and then if there's a WebSocket client that happens to be connected to this application, they get the stream, and we use JavaScript, D3.js, to draw pretty pictures. D3.js, if you're not familiar with it, it's just an open source library written in JavaScript. It's literally for drawing shit on the screen. People find it intimidating. It's not. It's just plain JavaScript code. I think this is code that's drawing a polygon of some sort, right? So it's very, very simple, just plain JavaScript code. But it lets me do stuff like this. So this was the first visualization that we produced. Taking that live stream of data coming in through the collectors and painting a dot on the screen at every geographic location where someone was consuming our data. So this is the first thing that I built that my boss was like, oh, wow, that's cool. And I said, that's not cool. That's a map of the English-speaking population of planet Earth. Because we're a media company, and about 99% of the content that we generate is either in English or Japanese. So there you go, right? What I didn't get, what took me a while to understand was that I'm looking at this from a very, very different perspective than the people who are actually generating this content. They're looking at this and they're seeing not a map of the English-speaking world. They're seeing, I did that. Look, I made content, and look, people are touching it. They're interacting with it. And this was an important moment for me because I had not considered previously the sort of emotional connection that people can make to data when it's presented to them in a way that their brains can process, right? So I think this is very, very exciting, and it's cool to be able to work in stuff like this. I tried a couple of things to make this data more useful. I call this the Dippin' Dots map. I don't know if it's going to play here. It might or it might not. Essentially what I did here was color code all of the dots based on the property, whether it's daily finance or Autoblog or whatever. And there's nothing in here, again, that is mind-blowing. Like daily finance is one of our brands, and they cover the stock market and investments and stuff like that. And not surprisingly, it's really popular in New York and Chicago and San Francisco. Engadget is really, really popular in Silicon Valley, in the sort of like the tech hubs, Austin, Nashville, New York. Autoblog is really, really fucking amazingly huge in Russia for some reason. They're like really into reading about cars in English. Right, so D3 lets us build these sorts of visualizations pretty easily. I'm going to include this. I think I might have locked my slides out. Yeah. All right. Oh, there's the dots. OK. I included this slide just so when you go and look at these slides afterward, after you've rated this talk on Joined In, you can just keep a bookmark to it. If you ever need to calculate the position of the vertices of a regular polygon, given the center point of the polygon, that's how you do it. Another visualization, and this is actually the most popular visualization that we have, is something that I call the Pageview Heartbeat. And usually it's not blown up huge like this. It's just tiny, and we put it next to the post. I show you this to point out that this is not data. It's generated from data, but this graph doesn't have any numbers on it. This is not useful information. But it looks kind of like a heart rate monitor in a hospital. And it peaks and it troughs, and most of these peaks and troughs don't even really mean anything. A lot of times it's just the network glitching out for a microsecond. But putting this next to a post gives the people who put their heart and soul into writing that content this sort of immediate emotional feedback that lets them kind of connect to the fact that there is this whole world of people out there who care about what they're doing, and that's important for them. And kind of keeps their energy level up and keeps them creating cool content so we can sell you more tampons. This stuff also lets us do things like multivariate testing. What's cool about this multivariate testing is because it doesn't need to be staged, editors can create tests for their content without talking to a developer. They can just go in there and say, OK, I have this article. I'm going to try 3 different headlines for it. See which one performs best, and throughout the day, if I see one that's performing way better than the others, I'm going to bump its weight up, so it's going to get all of the traffic, or the majority of the traffic, right? And they can do this immediately. They can get this feedback. Basically, when they hit publish and then jump over to this screen, they start seeing the numbers change immediately. I mentioned briefly before that we're talking, so I'll give you the very, very short description of what the media platform is. Essentially, it's a CMS. That stuff gets stored in a database that they generate content, and then we have this huge, huge rendering farm that renders content. And you can access that content if you're Engadget or one of our brands in one of two ways. You can pull it out of an API and then do whatever the hell you want to do with it. Or you can build your application, build your website inside of our walled garden using a custom DSL that's based on Twig or built on Twig called Code Blocks. Right? And that's what the majority of our brands do. They are developers. They need profiling tools. They don't have it because we're making them write in a made-up language that we invented, so there's no cool tooling around it. So we wanted to build them a profiler. Right? So this is something that's modeled after the Chrome inspector. This is another instance of how we're using data to sort of make the jobs of our content creators easier. Now our site developers, our web designers, can write some code. They can run it live in the platform and immediately get feedback as all of the different pieces of it run, right? And so this is another data problem. What I found is like when you start looking for data problems, you find them everywhere. What I find is interesting, like how many people are wearing a Fitbit right now? Like this is a data problem. There's data, like, you have these 3 accelerometers in here that are like calculating where your arm is moving and just generating this huge stream of numbers. If you ever looked at the raw data from a Fitbit, it's just fascinating. It's just this huge, huge streams of numbers. And by looking in those numbers, you can find these patterns, right? So we're doing the same thing here with profiling and with looking at these patterns, usage patterns. It ended up being a fairly simple application with a somewhat complicated structure, and there's lots of pieces of it laying around. I only covered a handful of them. We're constantly adding new things to this platform. But essentially, we have this receiver layer, which is a transit. And we have a processing routing layer, which is a transit. And all this goes into a storage engine. Right now, ElasticSearch, but now also Vertica we're using. We're looking into actually using Spark on the back end of this now, right? So it goes into all of these different storage engines. The important thing is that all of these different layers are geographically decoupled. They live in Amazon. They live in AWS. They live in our iron in the basement, right? They're capable of being independently scaled. And they're completely encapsulated. They have no cross-layer dependencies. They're all using open protocols to talk to one another, which lets us build like with lots of cool tools, right? So the input streaming, like I said, is written in Java. All the routing and filtering is done in Node.js. All the aggregation, the multivariate implementation, like I said, our stack, we're a PHP shop. It's a PHP stack. All of the aggregation stuff is written in PHP. One of the big wins for Elasticsearch for me is that you can interact with it in PHP really, really easily, way more easily than you can interact with Hadoop. We're using JavaScript for the visualization, all the multivariate testing stuff. It's also written in PHP. Lots of things in here. So it took us 6 months to build this data pipeline. We have all of these entry points, user data collectors and application code. That was really the easy part. Now we have the framework to start answering some of those cool questions that I kind of hinted at. So some of the things that are up on our plate, live debugging and runtime profiling, I've just been able to cross off because we have that now in production, which is awesome. We want to be able to embed these visualizations directly in the tools that our editors are using. On-demand stream filtering is something that we have on the plate for the end of the year. We want to be able to actually take that live raw stream and apply filters to it. So we can actually let people deploy their own data collection and management platforms, right? So we're building a framework for them. We want to be able to do predictive performance analysis. This is a big goal for us for the next year, is to be able to take a piece of content and predict how well it's going to do, and maybe make accurate predictions, hopefully, about how it's going to do. And then doing real-time sentiment analysis. We're really lucky in that we actually have an amazing team based out of Tel Aviv, and all they do is work on this amazing machine learning platform that does sentiment analysis, right? So we have access to these people, and we have access to their awesome technology. We want to start doing that to sort of monitor and try to quantify how people are receiving and using our content so we can help editors make better decisions with it. So I hope that next year I can come back to ZenCon and tell you about some of that stuff. In the meantime, thank you for coming up at 8 o'clock in the morning to listen to this talk. I'm sorry I'm not Yitz, but reach out to me at IEKillerBees on Twitter if you have any questions about this, or if you just want to talk about this. This is basically what I geek out on these days, so I love talking about this, and if you're trying to think about how you can handle some data problems in your work or in your projects, I'd love to talk to you and kind of get your feedback and share ideas. I would really appreciate it if you go on to Joined In and give me some feedback about this talk. It's important for me. It's important for all of the other speakers that you've seen here throughout the conference. We actually do pay attention to your feedback, and it's important for us. We really, really need it to help us get better. We want to make sure that you really enjoy these presentations and keep coming back year after year. So please definitely hit joined in. I don't know if we can take questions in this room, but thank you.